Homework 3, problem 4, find the electric potential V everywhere for a uniformly charged sphere. Now, the method we're going to use to solve this is we're going to use Gauss's law. Find the electric field, and then integrate find the potential. And the rule we're going to use is that the potential V as a function of position is minus the path integral, dl dot the electric field, where the path that we take is from some reference point to the point that we're interested in. We have spherical symmetry here, so it turns out that our reference point, of course, is going to be infinity. Now, I said we're going to use Gauss's law to find the electric field for the uniformly charged sphere. Luckily, we've already done that. Going back to problem 1, Gauss's law for the uniformly charged sphere gives us this result, so I'm simply going to copy that down for this problem. And so the electric field that we'll be working with is this. So there's the electric field that we will be working with. Now we simply have to evaluate this integral. Now this integral can be needs to be evaluated in two parts. If our r is greater if our little r is greater than big R, then we only have to integrate over a single thing, so that can be done in one step. So we're going to do that first. If r is greater, the magnitude of r is greater, capital R, then we're going to evaluate it in one step. Now, since we're integrating from infinity, we're going to integrate along a radial direction such that the dl, the direction of dl, is in the r hat direction. And so we're going to get that the potential V, now as a function of r, not a vector, now only as a function of r, the radial distance, is going to be equal to minus the integral from infinity to little r, dr prime, of e sub r. E sub r for us, we only have the one region, so this is rho naught over 3 epsilon naught, r cubed over little r prime squared. I can bring that part of it outside the integral, and the integral of 1 over r squared, or minus 1 over r squared, is positive 1 over r. So this will be rho naught, capital R cubed, over 3 epsilon naught, and then I'm going to get a positive 1 over r prime evaluated at r and infinity. The infinity is going to give 0, so this will give me a positive rho naught, capital R cubed, over 3 epsilon naught little r. And so this is for r greater than r naught. If r is less than r naught, we have to break this into two steps. So the potential will be broken into two integrals, the integral from negative infinity to capital R, dr prime, rho naught over 3 epsilon naught, capital R cubed over r prime squared, plus the integral from capital R to lowercase r, dr prime, rho naught over 3 epsilon naught, little r prime. So the first integral is fairly simple. The first integral is just going to be that evaluated at capital R, so that'll be r cubed over capital R, that'll be r squared. So it'll be rho naught over 3 epsilon naught r squared. For the second integral, we're going to get a 1/2 r squared evaluated at that point minus that point. So plus rho naught over 6 epsilon naught r squared minus capital R squared. Combining these together, we're going to get rho naught over 2 epsilon naught r squared minus rho naught over 6 epsilon naught little r squared. And so that's in that case. Writing them both together is going to give us the solution that V, now everywhere, is just going to be combined for these two things. It'll be rho naught r cubed over 3 epsilon naught r for r greater than capital R, and it will be rho naught over 2 epsilon naught capital R squared minus rho naught over 6 epsilon naught little r squared for r less than capital R. And there you go. So that is the potential everywhere. The last thing it says to confirm that we get the electric field by taking the gradient. And so the minus gradient of this potential is, of course, minus partial with respect to r of this potential as a function of r alone times r hat. We can go ahead and do that. The derivative of 1 over r is minus 1 over r squared. With a minus, that'll give us a positive. And so for part of this, we're going to have rho naught capital R cubed over 3 epsilon naught r squared r hat, and this is for r greater than r prime. And for this one, it'll only be this guy, so the derivative of r squared is, of course, 2r. So this will be, and the minus will cancel with that minus, so this will be rho naught over 3 epsilon naught r vector. And this is for r less than r. And I would just like to point out that the green equation here is exactly the same as the red equation that we started with. So we do get what we should.